All right, welcome to a tutorial on combination circuits. So I'm going to show you what a combination circuit looks like. You saw one from the FET tutorial. I'm going to show you how to calculate the effective resistance of that circuit, and then we're going to fill out a Verb table, which looks at the voltage drop, the current, and resistance of the circuit and the individual resistors. And then the rest of this you can work on in practice on your own. Okay, so let's look at this circuit right here. Let's make sure we understand why it's a combination circuit. Easiest way to understand it is always start at the voltage source and see what happens from there. So I'm going to start here at the positive terminal. So I follow current or charge pass. It has to go through the 6 ohm resistor, so it's in series with the battery. And if I'm going to eventually come back, I have to pass through the 10 ohm resistor. So these two are in series with each other and the battery. Okay, now what happens here, and this is where students get confused, is with these two. We have to recognize that right here or here, doesn't matter, is a junction, because current is going to split into these two branches because there's two alternative paths, and then they come back together right here. So since they split, then this 60 ohm resistor is in parallel with this lower branch. And so I have a series that splits, and these three are in parallel with each other. So that makes it a combination right there. And then it gets a little bit more complicated in that in the two branches, this is by itself, so there's nothing else to talk about, but these two are in series with each other. So these two are in series that are part of a parallel branch, and this parallel branch, if you will, is in series with these two. Hence we have a combination circuit. So walk through that conceptually in your mind and make sure you understand what's going on, because everything that follows is determined by your understanding of those connections. All right, so let's figure out the effective resistance of the whole circuit. In other words, we've got a 10, a 6, two 20s, and a 60. What does it quote unquote total up to? And it's not going to be the sum of those two. Well, the basic approach is to take everything that's in series with the battery and simply add them. So we know that the resistance is going to be 10 plus 6 plus the contribution of these two. So it's going to be at least 16. And as I said earlier, these three are in a parallel branch, but they're in series with these two. In other words, if I can take these three, reduce them to one resistor, one resistance, and I connect it like that, then I have a series circuit. Okay, so that's the idea. So let's approach this. So let's take the three resistors there and reduce them to one resistance. Well, it's easiest to start with the lower branch because the lower branch is in series with each other. So the 20 and 20 are in series, so they effectively become a 40 ohm resistor. Okay, so over on the right, I'm showing you the approach to the solution. So the 20 and 20 ohm branch reduces to a 40. And this branch is in parallel with the 60. Right, we talked about that. So we have to take the 40 and a 60, which are in parallel, and find their effective resistance. Well, the equation for effective resistance for parallel, I'll do it up here, is 1 over 40 plus 1 over 60. All right, common denominator for these two is 120. This becomes 3 1/20ths. This becomes 2 1/20ths. 3 plus 2 is 5. So this becomes 1 over 5 1/20ths. You do the math, and that gives us 24 ohms. Oops, I should write it here. So the three resistors that are in this part reduces to 24 ohms. Again, double check that yourself to make sure you get that. And we said earlier that's already in series with the 10 and the 6 ohm resistor. So I've taken this whole thing, I've reduced it, and I can't really draw it here, so I apologize if it's getting kind of messy. But let me change color. I've basically reduced those three to a 24 ohm resistor. Okay, and so now I've got 24 plus 10 plus 6, and that gives us 40 ohms as our effective resistance for the circuit. Okay, now I'm going to let you try one on your own. Let's say we change the circuit subtly. Let me erase all this. Where we short in one of the 20 ohms. So recalculate if there's a short circuit in one of the 20 ohms. Now let's make sure we understand what that means. That doesn't mean we remove it. If we remove it, we just removed it. A short means this resistance goes to 0. Okay, something happened to that wire that this now has 0 resistance. What would be the effective resistance of this circuit? Okay, I want you to think about how you'd approach that before I start again. Okay, so we have very similar circumstances. The 10 and the 6 are still in series, but now they're in series with two resistors, the 20 and 60 in parallel. Still a combination circuit. So all I have to do is find the effective resistance of 20 and 60 in parallel and then simply add it to the 10 and 16. If you did this already mathematically, you should have gotten an answer of 31 ohms. Okay, if you didn't, well, let me show you. So it's 10 plus 6 plus the contribution of the 20 and 60. I'm just going to do it here. They're in parallel, so that's going to be 1 over 20 plus 1 over 60. That becomes, these two add up to 16, and I'm sure you can work out that these add up to 15. Okay, 1/20th plus 1/60th is 4/60ths, which is 1 over that is 15. So we get 31 ohms. Again, make sure you can do that. Don't just take my word for it. All right, another problem to try. Instead of shorting out the 20, let's say it's restored back to its normal, we short out the 60. Okay, so it's not removed, it's just shorted out. 0 ohms. Okay, what would you say happens? I'm going to guess a number of you said we have the 10, 20, 20, and 6 are now in series, so our effective resistance is 56 ohms. That would not be correct. If we remove the 60, then you'd be fine. But since this has 0 ohms, this short is what's going to happen is all the current, let me actually change color here, is going to be like this. It's just going to go through that upper branch because it's shorted and ignore the lower branch. So for all intents and purposes, this lower branch has an infinite resistance compared to this. I know it's not literally infinite, but it's comparatively. So basically what I have is 10 plus 0 plus 6. So the effective resistance is 16 ohms. Okay, so understand the difference between removing a branch, which basically makes it infinite resistance, or shorting it out, which makes that part 0. It's a subtle difference. Okay, so let's finish up by doing a Verb table. And I haven't done this beforehand, so it might be a few stutters here. So here's, I've listed all the information we already have. We know we have an EMF of 120, and we've got the individual resistances. I'm really interested in filling out this part here. You can always do power later. That's easy, because you have 3 equations that allows you to do that. Okay, so anyway, let me see if I can get part of the circuit in there along with the Verb table, because I know I'm going to have to refer to it, and this scroll button is not working very well. All right, well, that's the best I can do. So I know where to start with this one. It's like a Sudoku. You've got to figure out what you have and where to work with. We already figured out the effective resistance is 40 ohms. So right away I can use it. So across we can use Ohm's law, vertically loop rule, junction rule. Okay, and we've already got the resistances. So across, I know I have to have 3 amps in the circuit, right? Ohm's law, 120 divided by 40 gives me 3 amps. Okay, so if I know I have 3 amps, then I can figure out the currents through some of the branches, right, or some of the resistors right away, right? I've got 3 amps here. That's what it means to have a current circuit, a circuit current of that. So I have to have 3 amps through the 10 ohm resistor. And when I come back around, I know I can't see the other ones, I have to have 3 amps in a 6 ohm resistor. So right away I can do Ohm's law, resistance of 6, 3 is 18 volts here, and there's 30 volt drop across the 10 ohm resistor. Okay, now it's going to be figuring out what to do with these two. So what I want to look at is what's their relative, there's a number of approaches I can do here. Okay, in fact I'm going to see if this approach makes sense. If I just figured out I have a 30 volt drop here and a 18 volt drop here, then by the loop rule, this is 120 volts, the drop for any any loop has to be 120. So if I take a loop, and let's say it looks like this. Let's say I'm going to make the upper loop. I'm going to do this as one of my loops for the loop rule. The total drop across all resistors has to be 120. So this is 30 already. This is 18, that's 48. So that leaves this one to be 120 minus 48, which is 72 volts. So there's a large drop across that upper branch. Okay, so let's fill that in across the set. This is going to be 72 volts. And if that's 72 volts and that's 60 ohms resistance, then my current through there is going to be 72 divided by 60. Okay, so I don't know what that is off the top of my head. Let's see if I can get my handy calculator out. 72 divided by 60 is 1.2 amps. All right, so we know it's got to be less than 3, so that's good that we got 1.2. Okay, now the other two should be relatively simple to do because I know that I have 3 amps coming in to the branch, to the junctions I should say, and then I know this upper one has 1.2 amps. So if this has 1.2, that means this branch has to have 1.8 ohms, which makes sense. The effective resistance of the lower branch is 40 ohms, and so it has less resistance in the upper branch, so it's got to get more current. In fact, it should get, the ratio of the resistances is 2/3, so it should get 1.5 times the resistance, or excuse me, the current. So this is going to be 1.8, 1.8. I don't need the circuit, well, maybe I will later. So now the voltage drop, 20 times 1.8, that's 20 plus 16, right? 36, 36. Oh, look at that. The voltage drop across the 220s adds up to 72, which is the same as the upper branch, which we'd expect from the loop rule. So let me show you that if you're not quite following. We know we have a 72 volt drop across here, so by the loop rule, another loop we could do, I have to have a 72 volt drop across these two. So this one gives me a 36 plus another 36, and they all add up to 120. So everything comes together beautifully in this example in terms of the loop rule, the junction rule, and Ohm's law. Okay? So we've already shown the loop rule is obeyed, but you might want to show that mathematically. So I want to introduce, before we're done here, one last problem I want to set you up on because it's a nice problem. Suppose we have 4 identical resistors and they happen to be 12 ohms. There are 10 unique ways you can connect these that would give you different results in terms of voltage, current, and power. I've drawn one such combination. I'm not going to draw a voltage source, but we're going to assume this is eventually connected to a voltage source. Okay, but you don't have to draw that. It's not necessary. It's assumed. Okay, so I want you to draw 5 unique ways, or actually 4 others. And actually, I'm going to put a stipulation on that. I'm not going to let you do 4 in series. That would be another easy one. 1, 2, 3, 4 in series would be another way we could connect them. All right, and their effective resistance would be 4 times 12, 48 ohms. So I'll do that for you. And the other more obvious one is if I put them all in parallel. So I could have 1, 2, 3, 4, right? Connect them in parallel. And the effective resistance would be not 12 plus 12 plus 12, but 1 over 1/12 plus 1/12 plus 1/12 1/12. Or the shortcut again would be I have 12 ohms divided by 4 resistors, so the effective resistance would be only 3 ohms. So this gives you the maximum possible resistance for 4 when they're in series. This gives you the minimum. All the other combinations will give you somewhere between these two. So I want you to come up with 4 other ways you could connect 4 resistors that are different than these. All right, there's 10 overall. We've got 3 here, so that leaves 7 more. I've given you 1, so you've got to come up with 4 of the 7. All right, it's a good little challenge, and then there's some math problems I want you to do with that.